Hello, my name is Nolan Gutierrez. I'm going to be presenting visual reinforcement learning with imagined goals. So first I wanted to ask some possible questions. So what is the goal of an autonomous agent? So we want our autonomous agents just to be able to mimic humans. We want them to accomplish goals that normally we can do, but they can't. So one of the things we might think of is how can we get an autonomous agent to accomplish more than one goal? The standard in reinforcement learning is we only give our agents, our learners, a single goal, and they have to be able to think about how they'll solve that goal. So how, or get to that goal. So how can embedding input observations or states into lower dimensional spaces help us? So this just means that if we get our input observation, which might just be like an RGB image, we might want to compact it, make a compact representation, which is a lower dimensional space. And that would help us reduce the amount of hypotheses, so the amount of parameters that we have to search in order to have an agent that gets a good solution, that gets a good answer to how to get to those goals. So what does it mean for a machine learning algorithm to be unsupervised? So in machine learning, if you're unsupervised, it just means you're not giving as much information to the agent in order to accomplish its task. It kind of figures things out for the most part. In reinforcement learning, we're actually working with semi-supervision, where you're specifying a reward function, and this reward function is going to help the agent learn how to solve a problem. So it's called semi-supervised because this reward function has to be thought of by the designer of the model. So the goal of an agent in reinforcement learning is to maximize the expected sum of discounted So this, if you look at this reward function, it's just the average sum of rewards. This factor gamma just means that you don't care about as much about the future. So the future becomes less and less important. This expectation just means you're taking the average. So the aim of this paper is to have the agent learn a policy that can solve a variety of tasks. This can be done by conditioning an agent's policy and reward on goals, optimizing the expected return with respect to a goal distribution. So this inner expectation, this inner average, is just going to be your average reward given a policy. So just like a policy just means what action do you take in each state. State space from the environment, and your reward function. So this average usually only depends on these three things, but so what we're dealing with universal value function approximators. That just means we're dealing with multiple goals. We have to think about 4 different things. So reward, state, and action, and a goal instead of 3. In order to enable sample efficient learning, the authors employ a goal condition Q function. One can train an approximate Q function by minimizing the Bellman error. So if this is your error and you want to minimize this, it just means you're minimizing the difference between these 2 things right here. So this is your target. So this target's usually going to have a better idea of what the value of a certain state, or the value of taking an action in a certain state is. So this function right here just means you're using these parameters W. These parameters just, they better help you. Like, we're trying to optimize these parameters. So these parameters are actually what decides the value of your taking an action in some state with the current goal. And you're trying to minimize this error using these parameters. And this function right here just means you're taking the maximum value of taking an action in a successor state with the current parameters multiplied by a discount factor, which just means you're not going to care as much about the future, because this, and then the current reward. So this is called the Bellman error. So the authors chose to map states to latent distributions using a variational autoencoder. The structured code produced from this autoencoder gives a latent representation of the state space for the goal condition Q function approximator to operate in. So the encoders and decoders are trained jointly to maximize this equation, this loss function. So a loss function is just given these current parameters, what is the error. So this SI is the actual representation. So we want to minimize the difference between this actual value and the produced value, which is Z, or which is the posterior, this posterior distribution for the decoder. So this side's called the reconstruction loss. That'll make sense in a little bit. This is the KL divergence. So all we're doing is making sure P of Z is close to this. This is a posterior distribution. That just means you're trying to make it closer to something called a sparse network. So a sparse network just means you try to make most of the parameters that you use for your model close to zero. It helps your computational time. So P of Z is called a prior. This is a posterior distribution. P of Z is going to be called unit Gaussian, which is just a probability distribution. DKL is the Kullback-Leibler divergence. Beta is used to constrain the variational parameters of the variational autoencoder. The encoder Q parameterizes the mean and log variance diagonal of a Gaussian, while the decoder P parameterizes a Bernoulli distribution. Parameterization corresponds to training with cross-entropy loss on normalized pixels. So that'll make sense in a little bit. And this Z, so I'll get to that soon. So your DKL ensures that the Q stays close to the prior. That just means that you make them similar. We're minimizing this loss function, so we're going to be minimizing this, which is we're maximizing this, okay, which is a unit Gaussian. Z reparameterized in this case is in this deterministic equation. It just means deterministic just means 100% probability of something happening. Stochastic means you're adding some uncertainty. You're not sure. Where E is a unit from a unit Gaussian. since X is a sample and G is deterministic, we know that Z is also a Gaussian. So this E and Z have the same probability distribution. So now we're going to look at the overall structure of this variational autoencoder. So this encoder parameterizes a Gaussian distribution, which takes two parameters. It takes a mean vector and a sigma vector, which is a standard deviation. And using that deterministic function G, this is G, we're going to create a sample latent vector, which the decoder will try to use to recreate the output. So using that loss function from earlier, we try to make sure these two are identical, the X dash and the X. Remember, this is a decoder, encoder. This is the compact representation. So now I'm going to talk about sample efficient RL, reinforcement learning, with learned representations. The authors train a twin delay deterministic policy gradient on the latent representations of the state and goals using the encoder of the variational autoencoder. So this just means we're using this model to try to take actions in an environment. And this model is only going to use states produced from the variational autoencoder, which produces that compact representation. So this is only going to use that compact representation to try to accomplish its goals. So the mean of the encoder is used as a state encoding. The authors train a beta VAE by executing and collecting state observations. Only after training the beta VAE is the goal condition Q function trained in the latent space. So it just means you have to train the autoencoder before anything else happens, before you can try to take actions before you can try to solve the problem, get to your goal. So now I'm going to talk about reward specification. The authors had to create their own reward. Usually you try to use the difference between images, but if you think about taking a picture of two images, the two images don't necessarily mean you're taking a picture of the same environment. You might be taking a picture of a mural and the actual real life. So the difference between those images doesn't always mean that they're this, like a low distance, a low air doesn't always mean they're the same image. So the authors use this thing called the Mahalanobis distance in the latent space for a goal condition reward. The authors note that the matrix A is an identity matrix, which is just a matrix of zeros, or a matrix of zeros where the diagonal is 1 or are ones. And this is and they also found that having A as the identity matrix makes it close to that original Euclidean distance, and it actually had good results that they found. So while embedding the goals and states into the same latent space improved the sample efficiency, the authors also used latent goal relabeling on explored states. So the author sample goals from a diagonal Gaussian fitted to the latent encodings of the VAE training data in order to obtain goals and rewards for each sample. The reward for each sample is computed using the Mahalanobis distance in the latent space. So what this just means is you have if you could think about in the real world, you have your history, you have your past, and you might try to imagine how your actions would have been different in the past given your current goals or given new goals. You try to imagine different goals in the past and what you would have done differently. So the authors again sample goals from a variational autoencoders prior to allow for the agent to perform self-supervision, where the self-supervision comes from the agent proposing its own goals from the learned latent representation. So that just means it's using that compact representation to try to think about what the value of taking an action in some position or state is. It's using a code, a code word. So reinforcement learning with imagined goals. This is the actual algorithm. So all this does is you take an action, you get a position from the environment, you store your history right here. You get a random transition, you get a random past experience. You're going to make it more compact. You're going to compute a new reward, and you're going to try to minimize that loss function. You're going to minimize the error between what your thoughts are and what the actual answer is. And then this is just more sampling. So you're trying to given new goals, what kind of actions you might have taken. So how might this be useful? And could latent representations be used for any of the projects in the lab? Do you think goal relabeling will be more widespread in reinforcement learning? So all these questions boil down to, can we use this intuitive model, or we want an agent or a learner to try to imagine more scenarios about its past given its current thoughts about its goals. So it's very intuitive. We can think about how this relates to us in the real world.